In this video, we will introduce our paper, Rethinking Pose Estimation in Crowds, Overcoming the Detection Information Bottleneck and Ambiguity. Multi-instance pose estimation aims to detect each individual with all their visible body parts. One major challenge is the frequent and close interactions between individuals, especially in crowded scenes, leading to occlusions that complicate accurate localization and body part grouping. Pose estimation is approached in two different ways, top-down and bottom-up. The top-down pose estimation approach first detects each individual and then estimates the pose, ensuring that each person is distinctly recognized. This method excels in scenarios where individuals are clearly separated, providing high accuracy and detailed pose information. However, in densely crowded scenes, top-down methods are ill-defined as it is unclear which pose should be predicted within a bounding box that contains multiple individuals. This is where the bottom-up approach is usually better suited. Bottom-up approaches estimate all body parts in the scene first and then group them into individual poses. For this grouping, various methods have been proposed in the literature. While bottom-up methods are better at handling crowded scenes, they can also struggle to correctly group body parts. Another advantage of bottom-up methods is that they do not require a separate detector. Building on the strengths and addressing the weaknesses of both top-down and bottom-up methods, we propose a hybrid approach, BUCT. This bottom-up condition top-down approach, in short, BUCT comprises two stages. In the first stage, instead of using an object detector, we use a bottom-up or single-stage pose estimator to get the predicted poses. We then compute the individual box from the poses. Furthermore, we adapted top-down methods into conditional top-down methods, which do not simply take an image crop as input, but also an input pose to condition the pose prediction on. In the second stage, we feed the individuals and the predicted poses, which serve as conditions, to the pose estimator to get the final pose. Thus, BUCT addresses the inherent information bottleneck between a detector and top-down model. The second stage, the CDD model, can be implemented in different ways and is thus flexible. CDD with pre-net. Given an input pair containing the image and input condition, we feed them in parallel to the convolutional layers to extract features. Then we feed the fused feature to a vanilla HRNet. We also modified the transpose to leverage the conditions as the side information by concatenating condition-specific tokens to this transformer input sequence. Furthermore, we added an attention mechanism to a TD model to learn a better representation and leverage the information from the conditional input. We propose an architecture comprised of a conditional attention module and HRNet, where we feed the input image and the corresponding pose condition into HRNet and the COM in parallel. The COM can be inserted after any HRNet stage and its output is fused with the features of the corresponding stage. We tested the different variants of BUCT on crowd pose. We found that CTD boosts crowd pose results using conditional inputs from different bottom-up and single-stage models. Thus, combining visual and geometric information can flexibly refine pose predictions. We also compare BUCT with various state-of-the-art methods and found that it achieves better performance compared to other methods, including hybrid approaches such as MeetNet. To gain better insights into the performance gains of BUCT, we computed precision and recall on the crowd pose test set. We compared our model to the previous state-of-the-arts on crowd pose, MIPNet. Importantly, we have higher recall and precision than MIPNet for all BU models. Thus, due to its design, BUCT improves the precision and recall for all BU models we tested. We also test our models on OC Human and COCO. We achieve SOTA on OC Human, on the classic COCO benchmark that contains very few occluded humans. We also achieve competitive performance. With our hybrid approach, we can also substantially boost performance on the animal benchmarks, with especially large gains in crowded scenes. A qualitative example can be seen at the bottom. BUCT can accurately predict the poses of the two marmosets sitting closely together. In conclusion, we proposed a new hybrid approach to improve multi-instance pose estimation. Especially in crowded scenarios, BUCT is a simple yet effective method that can be integrated with many frameworks. We quantified BUCT on 3 different human benchmarks: crowd pose, OC Human, and COCO, and other 3 animal benchmarks. Thank you so much for your listening. More details can be found in our paper and the code is available online.